Welcome to Insight Builder channel, large language model automators, Python experts, and my dear friends. Quantizing LLMs and fine-tuning them, a definitive guide. In the last video, we have seen how to try and fine-tune a model, that is a large language model. And we saw the varieties of challenges that one can face from, the moment we try to load the model and to train it, and also to finally get an output, which actually may not be the way we want. Now, in this discussion, what we are going to do is we are going to take a bigger, large language models, and we are going to quantize it first, and then we are going to, try to understand how we can fine tune them. But before we, dive into this video, this is the overview that we will have. So, why and what of quantization will be explained. Following that, there will be hands-on quantization of Mistral or Gemma models, whichever is more feasible. We will be showing the challenges of what will happen if you try to fine-tune a quantized model. Most of you might be knowing it, but still, if you guys are completely new to this process, then you will see the errors. And we will be introducing the PEFT tuning and the task types, discuss on the LoRa config parameters. We will dive into the LoRa config and fine-tuning of Mistral 4-bit model. So that will be a hands-on in this discussion. So we will be diving into this, and later we will be looking into PEFT tuning and task types in a different video, because the way the task types and PEFT tuning methods works is a little bit different. It's called as prompt tuning methods. That will be taken separately. To begin with, let us dive directly into the notebook as usual. And if you have seen my earlier videos, so here is the same kind of a setup. You will have the GPU Nvidia SMI output in this window, and in this window we will have the varieties of codes that you are going to execute. So I'm going to try and zoom in. Yep, that looks better, I suppose, compared to the last video. This couple of information is missing in this location, but you don't need to worry about that. It's not going to be affecting your understanding. Let's continue with the code here. So what we are going to do is we are going to first of all understand what transformers version is available. I'm using 4.38.1, and if you look at this imports, you will be seeing that imports has been categorized into the purposes that it serves. So the first part of the import is more about loading the model and working with the data a bit. Second is purely about training. So it's about the trainers, training arguments, etc. And here is the data sets, loading the data set. And this entire group of imports is for PEFT related classes. And then finally we have various torch related imports here. So I would like to just go through the various classes that I imported here. So the auto model for causal LM will import the large language model and place a causal language model head on top of the model. Auto tokenizer will import the tokenizer. The bits and bytes config will help us in creating the configuration for quantizing the model. I'll be showing you the example in working. The default collator will help in collating the data and feeding it to the trainer. This should be ideally be here, and the get the linear schedule with warm up also should be ideally in the bottom training area. So that is something that I'm going to modify, because this is all related to the training, right? And once you look at these classes from this perspective of what they support or what is their purpose, then remembering them will be really useful and easy also. You already saw this load dataset is going to get the dataset, and this dataset class is going to take any kind of data loader or the dataset that you are having and converts that into a dataset type. So we'll be looking at that in action in a couple of minutes. When it comes to PEFT library, there are many inbuilt classes. Whatever you are seeing here is the various configuration that we can use for creating the fine tunable PEFT model. Again, I'm repeating, these configurations can be used for creating fine tunable adapters or models. So how to call them? So it is better to call them as adapters. The PEFT library will help you to create adapters, and these adapters can be trained, and later you can load the adapters along with the base model. So that is how the PEFT setup works, and all these classes support that. And these torch imports that you are seeing will support for the various additional or miscellaneous activities. Okay, now I am going to work on Mistral 7 billion model right now. I had tried working on various other models also, as you can see here. So I had tried Google Gemma, I have tried T5 large, but then I had faced considerable amount of challenges. So I'll be discussing about the challenges also. So obviously that is the main purpose of this series of videos. And so I finally resorted, okay, let us try with Mistral AI. And this Mistral AI 7 billion model was also used in the tutorials that was provided by the PEFT documentation. So after trying out all this stuff, once I was unable to come up with a solution, then I decided, okay, let me first of all introduce the challenges that I faced, and then also provide a various other additional information with a fine-tunable output. So that's how this video has come up. And the save location is going to be, I am going to make it as Mistral models. Right. So the names, variable names are self-evident. I am not going to explain them. I'm going to execute this particular first cell. So I'm going to execute this cell, and let me check it. Yeah, I'm going to execute this cell. So this already has been executed and the kernel has started. And I'm going to start importing starting the tokenizer. So this is going to get the Mistral AI tokenizer and create the tokenizer object. And here I am going to load the Mistral model. And this Mistral model is going to be first of all loaded without any kind of quantization. So take a look at this particular area. The memory consumed right now in the VRAM, that is the GPU RAM, is 19 MB. But the moment I try to load the model, the RAM consumption will start increasing. So there are two shards, checkpoint shards, that is already downloaded by me and placed in my local environment, and it actually becomes 10 GB. So I have a 12 GB 4070 Nvidia RTX card, and out of that already 10 GB of data is used up, meaning there is no way I'll be able to fine tune this model if I don't find a different way. So in the last video, you must have already seen that we can actually load quantization process. Next, what we are going to do is, I'm going to show you a different way of unloading this model. To unload this model, if you scroll down a bit, so I have various things here. So there is something called as moving the models. So if you click on this, you will see that we can actually move the model from the CPU, from the GPU to the CPU. So I'm going to open one more launcher, and I'm going to open HTOP here. So I'm going to move the model that is already inside the GPU to the here already there is almost 21.7 GB of memory being used. I think there is some rogue data is getting loaded here, so that's why you see this much RAM. Just a second. So I had looked at the notebooks, and I was trying to find out how the RAM, almost 32 GB of RAM I have got, and almost 21 GB has got used. So I wanted to check it. So the easiest way to check is to first of all close the kernel that you have started. So I closed the kernel that I had started, and I found that okay, the model that I had loaded here had been also loaded into the RAM. So let us try this again. The reason I am showing you all this the details is that there could be hundreds of reasons you will end up in out of memory issue. So we don't know about that. So that's why I want you to keep track of what is going on each and every step that we are trying to load the model. And one of the reasons is that when we try to load this causal model, causal LLM, it can actually go into the RAM and it can sit in the RAM there itself without actually releasing from the RAM. So let us actually load it right now. I'm going to run this particular cell where I'm going to load the model, and let us see. So it's actually first going into the RAM, right? It is moving into the RAM. Some parameters are not in the meta device because of offloaded to the CPU. So what is basically happening is, after 10 GB of consuming in GPU, there are still more data that is getting offloaded to the CPU also. So that is one of the reasons why we have been facing this issue. Okay, now that let us further move, and let me move the model to the CPU. I don't want this model to be in my GPU. So I'm going to execute this model to CPU. And the moment I do that, it is saying don't move the model when it is dispatched to multiple devices. So why is this telling? Because the model here has been moved to both CPU as well as GPU. So if you go up, if you look at it here, I have used device map equal to auto. So what has happened is this model is moved both to CPU as well as GPU. So I will not be able to move the model away from the GPU to the CPU. So that's not possible. So what to do? How to show you the alternate option? So for that, I'll be using a smaller model, so where you can see what happens. So now I am going to try to load the Big Science BloomZ 560 million. It's a smaller model, and we are going to try and load it into the tokenizer. Yeah, just a minute. I have to start the kernel, and I have to load the classes, and then I have to load the tokenizer, and you can see the tokenizer is getting loaded and it's ready. And now we are going to load the model. So before we load the model, the Nvidia card is free from any memory consumption, and you can see that the memory consumed is 2.3 GB right now, and here it's almost 2.2 GB. So now what we are going to do is we are going to unload this model that you have loaded here. This the object that is inside this particular memory, we are going to unload it. So how are you going to do this? So come here, and we are going to just say model.toCPU. The moment I say model.toCPU, you will see I have executed this cell. You can see that this cell is blue right now, but the memory is still not released. It is still there. So in order to do that, you need to then delete the model. Even then it will not go. After that, you have to empty the cache. So after you empty the cache, after you execute this, now you see that the memory has been released. Yeah, it's not fully released. It's not 19 MB back, but it's not 2.3 GB also. So this is how you actually release the memory. But yeah, it's a lots of hassle. And if the model is moved to multiple devices, like how it was happened in Mistral, then it is not going to be possible to release it like this. The only way to release it like the memory is to stop the kernel. Okay, let us go back to the htop. Just a second. In the htop, you will see that the model has moved to the RAM right now. So that's why the RAM consumption is actually on the higher side. Anyway, so that was something that I wanted you guys to understand before we go into the fine-tuning process. Right. Next, what we are going to do is we are going to continue with our discussion of why we need quantization, and why and what is quantization. So we already saw that we already saw that if the model is very huge, it will actually overflow from the device, and it will move to the RAM. So it will overflow from the GPU and it will move to the RAM. It's if it is a big model, and if it is moved to the RAM, then doing operation on the RAM is going to be very, very slow. It will be very difficult, even if your RAM is of high performance. So the alternate option is to quantize the model, and the quantization process, we can actually use it for both inference as well as for fine tuning. Once you quantize the model, so what will happen? So I'm not going to execute this particular cell where there is no quantization config. But if you look at this cell, there is almost 4 different types of quantization config. And the first quantization config is load in 8-bit. So basically it will load the model parameters and convert that model parameters to 8-bit version. In case of 4-bit, it will convert the model parameters to 4-bit version. In case of this BNB 4-bit use double quantization. So this particular option will quantize and do nested quantization of these parameters. I am not going to try to explain what happens in nested quantization. It's not something that you need to be really worried about. It actually doesn't give a lot of memory saving when you are working at a lower graphics card memory, like 12 GB or 16 GB. It doesn't make much of a difference. You are anyway not going to be able to fine tune very huge models. But if you are going to work with multiple GPUs with 16 GB 4 GPUs or 40 GB 4 GPUs like A40 and A100s, then yeah, you have to look at these things. But if you are going to work with single GPUs, it's okay. And finally, you have this both. You can incorporate all these things: load in 4-bit, BNB 4-bit use double quantization, and most importantly, you can say BNB 4-bit compute D type torch bfloat 16. So what will happen is when you are when you are giving this parameter, if there is going to be any compute done on the parameters, it will be done as bfloat 16. So the parameter will be of type bfloat 16. Bfloat is basically brain float. Brain Labs is a Google's research laboratory, and bfloat was discovered, or rather, the algorithm was created there in Brain Labs. So that's why it's called as bfloat. And this is all about the various quantization configurations that you can use. You have to use the bits and bytes config, and in order to use this bits and bytes config, you should install bits and bytes library. So you have to do a pip install bits and bytes library. You'll in the earlier videos I discussed about this. You can take a look at that. After you have executed this cell, what we are going to do right now is we are going to start loading each of these options and see how the memory performs. Okay, here you can see the nodes that I have created. Right, what I have been trying to do is whatever outputs that I am trying to get from the system, from my server, I am trying to make it as nodes and place it right next to my code. So in that way, what will happen is I can keep track of what I have done, and second thing is I can avoid doing the same mistake again. So most of the time what I faced is I worked on this single notebook for almost 4 to 5 hours, and I am glad that after working on 4 to 5 hours I learned a lot, and whatever I learned is there as comments here. So it actually gives you a sense of clarity, and also it gives you a sense of achievement. I mean, you are not wasted 4 hours, right? Just think about it. When you're going to sit in the morning 4 o'clock until 8:30, if you have achieved nothing, and if you are unable to fine tune a model, it's not going to feel good. But then I realized, okay, there are lots of things that you're learning, and you need to keep track of it. So that's one of the hacks that you guys can use. First, initially when we can use auto model for causal LM, we can load in 8-bit directly inside the pre-trained method. But now this has been deprecated, so you cannot use this. You need to separately call quantization config and send the bits and bytes quantization config. So it will be deprecated, so that's why I mentioned it here. And now I'm going to load the 8-bit version of the model. This is going to be Mistral model. Again, I have commented out the big science BloomZ, and I am going to load the Mistral model right now. So I have run this cell. I'm going to execute this cell. The moment you execute it, okay, what is the error? BNB 8-bit is not defined. So let us go up. Why the BNB 8-bit is not defined? I think I have not executed this. Okay, let me try it. Yeah, I think I have not executed it. Right now the model is again getting loaded, and you can see that the model is actually loaded in 8-bit here, and it is using almost 8 GB of data. Let us go to the HTOP, and here you see that the RAM consumption is not 22 GB at least, right? It means that the model is inside the GPU only. Initially, when we use this plain auto model for causal LM from pre-trained loading, it had offloaded the weights to the RAM. but now it is not. So yes, 8-bit works, but it's actually consuming around 8 GB. Whatever you are seeing here, this information is for Gemma model, not for Mistral model. So I moved to Mistral model because this is a bigger model than Gemma. So that's the idea. Anyway, so this is, you can actually make a note of it like this. You can just copy this and paste it here, and you can say 8 GB. Yeah, 8 GB, right? 8 GB and loading Mistral model. So you can say Mistral model. And when I was trying to work with the 8-bit model, and when I was trying to execute the training, it failed for various reasons. So that's something that I have mentioned here. We'll look at it slowly and steadily. Now that we have got the model trained, we will test this model to ensure that we are getting the output. And this is a basic function that tests it out, and you can see that this particular memory is getting used up, and we have the output. Good. So Mistral model is loaded, all well, right? Now let us do one thing. I want to see whether I can train this model. The model that I have loaded is based on 8-bit quantization. Where it is? Yeah, here it is, right? And I'm going to continue further. I have prepared this set of data, and this set of data is coming from the Dolly dataset. The same dataset that I had used for the earlier video. I'm using the same thing. I have also included an additional information here that I am adding a pad token to the tokenizer, that is Mistral tokenizer. I'm adding a pad token, and that pad token is going to be end of statement token, EOS. Okay, one more important point. In case if you want to add tokens, here I am just modifying the pad token to EOS token. If I have to add tokens, I have to create, I have to literally assign a new token, and then I have to add the token back to the tokenizer, and then I have to resize the token embeddings. If I don't resize the token embeddings, and if I go forward and try to use this tokenizer along with the model training, the model training will fail. This was one of the major challenges that I was facing in the beginning. Instead of using this process, try to avoid it as much as possible. But once you become really advanced in using these fine-tuning the models, then you will be using these things. So just keep in mind. But as of now, just go ahead and use this option. Further to that, I am tokenizing the dataset, and I am getting the dataset output here. So let me execute this, and it will get through, and you'll see that this is the dataset that I'm having, right? And you can look at the model memory here. So it's almost it is 8 GB, and you can see it's 9 GB here because it was used for inference. Once the GPU gets used, it does not release the memory back. So this is one of the challenges when you are working with CUDA related memory cells. So just be wary of it. If the memory is used once, and if you're going to start training, because of this 1 GB extra usage, your training can still go into out of memory error. This is one of the things. If you're going to go for training, do not do inferencing. Avoid inferencing. Okay. Once that is done, you can look at the model here. This is also one of the points that I wanted you to learn, because we are going to go into fine tuning using PEFT and LoRa methods. At that time, when you're going to go for LoRa methods and doing the fine tuning, you will be looking at these words: K projection, Q projection, V projection, O projection, and various other kinds of layers that is present inside the model. If you guys are totally new to these kinds of layers, you are not aware of neural network layers in PyTorch, I would suggest to take a look at my other videos in the playlist. You will come up to speed in no time. It's pretty simple, guys. It's Python classes. It's not the neurons that is in your brain. It's a simple Python classes made of arrays. In fact, tensors. We shouldn't call it as arrays, but it's made of tensors, and the tensors have an additional characteristics called as gradients. So that is what I want to introduce about these layers. But apart from that, I wouldn't want to dive deep. Yeah, I know it's not complete. But if you guys are new and if you are still intimidated thinking about these layers and all those stuff, just relax, go and look at the various other videos and also the documentation. You will find that it's pretty simple. Okay, now that said, let us continue. Now here you see that I have created a LoRa configuration already, but I'm not going to use this LoRa configuration right now. I have quantized the model and I want to use it directly for the training. That is my objective. So I'm going to come down here and in the training arguments, I'm going to remove this optimizer, and rest of the things I'm going to leave it as it is. So this training arguments will work, so should not be an issue. I'm going to create this data collator. That's pretty simple. And I am also going to change this model to regular model, the model that I've already loaded, but this is a quantized model. Keep that in mind. And rest of the things, the data sets, the data collator, the tokenizer, everything is something that you already are aware of. If you are not aware of it, take a look at my earlier video in this series. That will actually give you a good clarity. I will also attach that video in the description as well as in the links below. So let me execute the trainer, and right there you see that you cannot perform fine-tuning on purely quantized model. Please attach trainable adapters on top of the quantized models to correctly perform fine-tuning. So this is what I was talking about. So the trainer itself knows that this model that we sent in was quantized, and it is telling that I cannot do any training on that. So that is the reason why we have PEFT adapters. Okay, now let us go back to the presentation. So we have seen the why and what of quantization. Like, why quantization? Because if you're going to load the model, a very huge model, it's going to overflow from your GPU to the RAM, and if you try to fine tune that, it is going to be very, very slow. And inferencing, it's going to be slower. The reason for quantization is that you can reduce the size of the parameters by modifying the parameter type, that is the data type. You change it from 32-bit data type to 4-bit or 8-bit. We saw that using 8-bit quantization, we can actually reduce the model size and keep it inside the 12 GB GPU. That is a Mistral 7 billion model. We can reduce the model size to 8 GB and keep it inside a 12 GB RTX4070 GPU. You have understood why and what of quantization. But now you have also seen the hands-on of quantization for 8-bit. We will be also looking at 4-bit and also a couple of other versions in a couple of seconds. But you already saw the challenges once you try to fine-tune a quantized model. The trainer, the transformer trainer itself throws error, telling that you cannot fine-tune a fully quantized model. So this first 3 steps we have already completed right now. So let's move back to the before we move back, I want to introduce the LoRa config parameters and the various other ways of doing performance efficient fine-tuning. So PEFT is performance efficient fine-tuning. So let's dive into the LoRa config. LoRa means low rank adapters, and low rank adapters you can just a second. What you're seeing here is the documentation that has been shared by Hugging Face Hub on PEFT library, and this documentation is kept updated for every library release. And if you come to this documentation, if you look at the PEFT method guides, you will be seeing these 3 methods. That is prompt based methods, LoRa methods, and IA3 methods. I'll be sharing you this particular link also, so that you guys can later refer to. And LoRa method is what we are going to look into this particular video. So LoRa is a popular way to efficiently train large language models, and how it does is it actually decomposes the low rank decomposition of delta weight matrix to be learned during fine tuning. So this might look very scientific, and the theory behind it is not something that we are going to dive into. And apart from that, it's not just there is LoRa. So there is various other algorithms also, like low rank Hadamard product, low rank Kronecker product, adaptive low rank adaptation, and it goes on. there is never ending series of algorithms. But the point here is that the LoRa config or the LoRa algorithm will reduce the number of trainable parameters. That is what you have to take away from this discussion. Apart from that, the reason why I showed you this particular page is that you will see that this discussion on this page is more about doing the LoRa configuration and fine-tuning of a vision model. It's not for a natural language model. So I had reviewed this particular page, and then I have also tried to understand the LoRa config in this page. If you come to quantization, if you click on quantization here, there under the LoRa config, you can see the various configuration that you can do for the LoRa config. So that's the way I have tried to understand how the LoRa config works. Apart from this, I had referred to various Medium articles also. Medium articles are one of the very good source of information about fine-tuning and training new models. So do look at Medium articles on fine-tuning, and the Medium authors are really great. I'm really grateful to the Medium authors because they keep all the blogs regarding fine-tuning open to read for everybody. It's not made as the members only articles. So that's one good thing that I saw in Medium. So you guys can hit Medium and search for fine-tuning, and you'll see a lot of articles there. And yeah, even if you see a lot of articles, you are going to still face the challenges that we spoke about, right? Let's go back. So we were discussing about this particular challenge that we are facing, and we introduced the various PEFT options for tuning, and among them we have LoRa as the first option. So in order to initiate the LoRa configuration, we need to provide it some parameters. The important parameters are the rank, that is R, the target modules. The target modules are the modules that I spoke here. So if you scroll up, I told you to look at these modules, right? Q projection, K projection, V projection. These are the target modules that we are talking about. And these are basically linear 8-bit. So you can see that here. It's a linear layer inside it's a new linear layer neural network. And this particular layer is fully connected in this case, and it will do the necessary calculations inside the model. I'm not going to dive into the theory about these various heads. So the papers, if you look at the large language model papers, they call these as heads, and there is almost 32 layers of all these layers together, and each of these layers have in features of almost 4096 and out features also. So it actually changes here. So you can take a look at the out features and in features. Since I have zoomed in, it's not showing here, but you can take a look at it once you run this particular notebook. Fine. So let us now go back to the presentation, and we saw the target modules. Then we have the LoRa alpha. This is very similar to learning rate in the regular training. So usually we give the rank as 8, 16, 24, 32, and we keep the LoRa alpha either same as rank or half of the rank or twice the rank. So whichever way you can play with these things. LoRa dropout is the parameters that is assigned in the LoRa adapter. How many of those parameters will be trained? So if you are going to say 90% will be trained, then the dropout will be 1%. Sorry, 10%. So that you need to update here. And we have the bias, whether you are going to update the bias or not. So that is none, all, LoRa only, and the corresponding biases will be updated. And there is something called as rank stabilized LoRa. There is a paper on top of that. You can take a look at that. And modules to save, which modules you want to save in the final adapter. So all these things are provided, and all these things was taken from this particular location where it is. Yeah, from this particular location. So I had used the documentation only. It's not that I have made it up. It's all available in the documentation. But the point is, the documentation can actually make you to move from one particular page to another page, and it can be never ending. And whenever you are trying to get a model trained, and if you're facing an error, it can actually become really frustrating. So these are the things that I had faced, and I wanted to document it, at the same time share it with you guys. So apart from apart from LoRa, we also have the PEFT methods. I would like to dive into the PEFT methods a bit. I'll be discussing about it later in a different video. The PEFT methods, there is prompt, multitask prompt. P is prefix tuning. P is prompt tuning here, and we have prefix tuning. LoRa, we are going to discuss that. ADA LoRa, adaptation prompt, IA3, LoHa, LOKR, all these things we saw just now. And PEFT, the methods have various kinds of tasks. So we have sequence to sequence classification, we have sequence to sequence language modeling, causal language modeling, token classification, and question answering. Finally, we have feature extraction also. So this feature extraction is one of the tasks that will be used for embedding extraction, as well as it is used in the image processing also. Fine. So we have these methods, and we'll be discussing that later. Then there is another one, entirely different algorithm called as infused adapter by inhibiting and amplifying inner activations. Okay, this is completely scientific, and you can take a look at the paper. There is a paper attached to this particular IA3 also. But the point here is that fine tuning is more efficient with IA3, and it is better than LoRa. So that's what the paper claims. Just a minute. And how the IA3 makes the training more efficient, it reduces the number of trainable parameters. So you can see the various ways it does it here. And second thing is, it freezes the original pre-trained weights, so that the tasks that those weights can do is still remembered by the model. It's not modified. And also the performance of fine-tuned model with IA3 is comparable to the fully fine-tuned model, meaning without any PEFT. So it is comparable to that. And inference latency is not there. So these are the benefits of IA3. So this is something that I wanted to introduce about PEFT. I already have a separate video on PEFT, but that video is purely upon inferencing and loading the model, loading very big models. But here I want to introduce PEFT, the way to use the PEFT for fine tuning. Let's go back to the notebook. Okay, so that we have got some clarity right now. What we are going to do is, we are going to start from the scratch again. So what we are going to do is, we are going to stop the kernel, and we have tried to load the model earlier in 8-bit. Now we are going to load the model in 4 bits. Right, so just a second, let me execute this. And whenever you are executing this, ensure that the Python 3 kernel comes up here. If it states no kernel, then it means that cell has not got executed. That is one way to understand. Then we are executing the Mistral AI model. You should not execute this cell. You should execute this cell, which contains the various configuration, and then we are going to try and load the model in 4-bit. So this plain 4-bit, we are not going to do any kind of additional parameters. So we are not going to use this double quantization. We are not going to change the compute D type, anything. We're just going to do it as 4-bit. So let us come here. So this is the one. Again, load in 4-bit equal to true can be used in the past, but now it will be deprecated. So don't use that. Use the quantization config. So execute this, and you will see that the model gets loaded, and the model uses almost how many GB? So it's using almost 5.2 GB. So the 8-bit was using 8 GB, and this guy 4-bit is using 5.2 GB. So we can make a note of it like this: 5.2 GB, and as you see here, I have already made a note here that training works with Mistral 7 billion model. So with 4-bit, yes, it works. If you try to load the model by using any other way of quantizing, so for an example, if you use double quantization, or if you use this D-type, compute D-type torch bfloat 16, what happens is a very cryptic error gets thrown. So let me scroll down. Let me continue this continue this area. So I'm not going to do the inferencing. I'm not going to do the inferencing because I don't want to lose the memory. So if I do the inferencing now here, my memory will get used up. The VRAM will get used up. I don't want to do that. And don't move the model, do the dataset processing. So we have the dataset ready. You can look at the memory footprint. It's 4.5 GB. It's a bit off, but it's okay. And you can look at the model also. So this is the various model parameters. But now we are going to do the LoRa configuration. So in case of LoRa configuration, what we are going to do is we are going to use a rank of 16. So this is going to be a 16 rank matrix, LoRa matrix, and the alpha is going to be 16. I'm going to maintain it same. The target modules are going to be all this from starting from Q to all to up projection. So I'm going to do the LoRa on all the modules inside the model from Q to up down projection. So all the modules I'm going to quantize. I'm going to convert into low ranking matrix. Sorry about that. And also you can see that I have tried various other target modules also. So I want you guys to try this particular notebook by removing or uncommenting and commenting the various options that I have tried here and see what kind of errors you face, because I also explained the significance of each of this parameters here at the bottom itself that I showed you in the presentation quite some time back. But the most important thing is you need to see what kind of errors and how the trainable parameters get modified. Okay, so that is an exercise that I want you guys to try. I'm going to execute this configuration right now, and do not prepare the model for k-bit training. So this was one of the another challenge that I was facing. So if you prepare the model for k-bit training, the model, just a second, I am showing you a particular link. If you go to this link, you can actually look at this particular prepare model for k-bit training method. And this method wraps entire protocol for preparing a model before running for training. This includes these 3 steps. Cast the layer norm to FP32. Basically, it changes the parameters back to 32-bit. So it increases the size. It also it makes the embedding to require gradients, and it upcasts the LM head to FP32. So it actually increases the size of the model. And by default, when you do this prepare model for k-bit training, you'll see that it will take additional 2 GB of RAM. And this was creating a lot of headache when I was trying to understand this. So do not use this. If you don't use this, yeah, it is going to create a problem, because the training output that you're going to get in the beginning is going to be not good. But the idea here of this particular video is to first of all make you to understand how the training happens, and get a notebook or get a script where you can actually train a model first. After that, once you are able to train the model, you can get the resources like GPU from the Kaggle, or you can use Collab Notebook, or you can actually try to get your own GPU access from RunPod. But first of all, you need to be confident that yes, I'm able to run a basic trainable script, so trainable model. So this is something that I am having an objective. So you don't need to worry about how the accuracy will be affected by not preparing the model as of now, right? So I'm not going to run this cell. Okay, and now we already have the LoRa config, and then we can use the get PEFT model function that is imported from the PEFT module, and you can actually create LoRa model no prep. So this is going to be a model that has been not prepared. So this is a prep model. I'm not going to use this prep model. So it's a model that is not prepared, and I'm going to execute this. The moment I do this, you'll see that another 1 GB of RAM got used. Now I have a PEFT adapter. So this is actually an adapter that got created. And now if you come to LoRa model.noprep, you'll see that around 304 million parameters are going to be trained. Out of 7 billion, 3 million is going to be trained. That is around 4%. So that is the power of LoRa. So this is a low ranking attempt. If in case I had used the this option of quantizing, let me go up. If I had used this option of quantizing using double quant and also using the compute D type B float 16, then when I was trying to run the training, I was getting the error called as attempting to unscale FB gradients. So I was getting this error. When I was using a plain 4-bit quantized model, this error was not there. But yeah, if I am using any other option, it was getting an error. When I was trying to work with 8-bit quantization, the model was not able to run in 12 GB VRAM. So it was giving out of memory error. So you can see the point here. Now we are going to move to the training. So training, what I'm going to do is I'm going to open up these things. I'm going to make FP16 equal to true, excuse me. So I'm going to say FP16 equal to true, optimizer is equal to paged Adam W32-bit, that also I'm going to execute. And I'm going to say learning rate is equal to, learning rate I'm going to make it as constant, and that's not going to be an issue. So let me execute that. And I'm going to execute the data collator. And now in the model area, I'm going to use the LoRa prep model, right? LoRa model no prep. That is what I'm going to use. And rest of the things I'm going to leave it as it is. And once I execute this time, you'll see that the trainer did not throw any error. So it went through and the trainer has accepted the model and the object has been created. But whether it's going to train or not, so let us execute this. And you'll see that I am getting an error right now. So it's saying that input type into linear 4-bit is torch float 16, but BNB compute type is float 32. This will lead to slow inferences. And if you scroll down, you will see there is the same error, attempting to unscale from FP16 gradients. So this is one of the challenges that if you face, what I would suggest is remove this, okay, and redo the training arguments and initialize the trainer and then try to train back. Excuse me. So after further tweaking, the challenge of that the error that we are facing a second ago could be resolved by modifying that from FP16 we have to modify it to BF16 because we are using the brain float type. And also one more thing that I did was I went up and I had actually used the quantization config where this the compute D type of torch B float 16 was also enabled. So after I did this particular modification, the training started. Using this configuration of quantization and adding BF16 at the training arguments at the bottom, then the training started. And if you can look at it, it's using almost 11 GB of memory, and the validation is also getting started without any issues. I have given the evaluation strategy at 150 steps. So the steps is 150 here. So that's why you are seeing it. And I used a batch size of 1. If you look at it, most of the time I try to play with a very small batch size and number of epochs. That is because we are trying to learn. And the faster you are able to get the training and looking at the validation, the better it is, because you don't want to wait for one complete epoch and then see that the validation fails. So these things you can avoid by controlling the training arguments. Also, second thing is that never stop tweaking. So there are so many different options, but understanding each of these options is very crucial. Most of the times, even if you can take a look at the videos that is explaining to you each and every parameter, like how I explained in the beginning. So in the beginning, I explained to you what each of these classes are going to do, right? like this, even if you can look at each of these parameters and read through it, it is a good thing. Like here, if you go to LoRa config, I just read through whatever is written here. Even that is going to be very helpful for you. So do that, understand these things. If you are not able to understand, read it 2 or 3 times. After that, you will for sure understand. And once you start looking at the outputs inside the notebooks, it will be much more clear that why something is failing or what you need to modify in order for something to work. So let me start the recording after the evaluation is complete. Just to add one more point, you can see that the graphics card is running at full power right now. And also the graphics card is taking almost 65 degrees Celsius of temperature at this moment, even though my room temperature is almost 30 degrees Celsius, I should say, approximately 27 to 30 degrees Celsius. The graphics card is running hot. However, we can see that with proper ventilation and also with proper understanding, you don't need to be really worried about these kinds of things, but you should know what is exactly happening, and also understand that the more you are able to use your graphics card to its fullest extent, the better it is, because you have done your investment, right? The moment you see the training has been completed, the validation has been completed, there will be a momentary drop of this wattage. But anyway, here I couldn't actually show it, but if there's a drop in wattage, it's pretty normal, so you don't need to be worried about that. And yep, you can see that the first training has been completed. The training loss is showing no log, and there is a validation loss. So there you go. We have seen. I'm going to stop this training because I just want to show what happens. I'm stopping the training, and let us go back to the presentation. So in this discussion, we have started from the why and what of quantization. We went into hands-on quantization process, and we saw the various configuration of quantizing using bits and bytes. We saw the challenge that we face when we try to fine-tune the quantized model. Basically, the trainer does not allow you to do that. And we introduced the various tasks, the LoRa config parameters. Followed that, we went and worked on the hands-on LoRa config of Mistral 4-bit model, and then we trained it with the TF trainer. So we saw all these things. Also, we saw a lot of errors that we can face in case of the dataset. In this time, the dataset went through without any issue, but that will also be an issue in case of other training methods like PEFT tuning and task types. You will face that you have to provide the correct type of data in the correct format, or else PEFT tuning and task type method, that is prompt methods, will be much more challenging. So that is something that I've seen. And in the future video, we'll be diving into a different kind of a trainer that has been introduced by, again, Transformers library called as TRL. So there is a library called as Transformers Reinforcement Learning, and that library introduces a couple of trainers that we will look at in the next video. So till the next video, I would like you guys to enjoy the large language models and keep on fine tuning. See you guys. Have a great time.